Welcome to class period 4. Happy Friday. It is April 1st, and this is not an April Fool's joke. Thank you to Mr. Beauchamp for filling in for me this afternoon. My wife is not feeling well, so Mr. Beauchamp is graciously stepping in. And I thought I could do a quick recording of the lesson 11.6 about secant or secant lines. And I'm guessing you don't want to look at my face for that long, so I'm going to change that. Oh no, that's the wrong button. You really don't want to look at this. There, I think that's better. So, if you have questions from yesterday's homework, you can ask me on Tuesday, but let's look at our lesson from chapter 11 about secants. A secant line is a line that intersects a circle in exactly 2 points. So if we have a circle, a secant line would be one like this. So it intersects here and here. This is a secant line. That's different than a tangent line. A tangent line would intersect at just 1 point, like this one, if I could actually hit the circle. So this is tangent. So there we go. Draw a picture of a secant, contrast it with a tangent line. There are different properties with secant lines that we'd like you to know. So that's what the lesson's about. The intersecting secants theorem says if two secants intersect in the interior of a circle, so we have line, line, intersection inside the circle, then the measure of each angle formed is 1/2, get this now, 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. There's a lot there, so let's break that down. What that's saying is you have these two secant lines that intersect in a circle. The measure of this angle, for instance, is 1/2 the sum of the arcs that are intercepted by that angle. So that would be this arc is formed or intercepted by that angle. And the arc that its vertical angle intercepts, which is this one over here, right? This is the vertical angle. These are vertical angles here and here. So you would do 1/2 the sum of those two to get this angle inside there. Notice this is not a central angle. It is not hitting at the center. The center is right there. It's just somewhere, the angle is formed somewhere inside the triangle when two secant lines intersect. So I'd encourage you, if you're watching yourself, or I'd encourage Mr. Beauchamp to pause the video and see if you can answer questions A, B, C, and D, and you can feel free to work with a neighbor. And we're back. To find JKL, you would take the sum of the arcs that are created and divide by 2. I got 49.5. OKP is a vertical angle with that, and you're going to have the same calculations, so that answer is the same as before, 49.5. To find OKJ, you're going to take the sum of the arcs that are formed by that angle and its vertical angle, this one and this one, and divide by 2. So that's what we get right there, 130.5, and LKP is going to be the same measure. And that is an example of the intersecting secants theorem, secants that intersect. If you'd like, again, you can pause the video and see what you think you and your neighbor can work on number 2 and number 3. Pause the video and we'll be back soon with answers. Number 2 says find the measure of angle 4, which is in here. It would be nice if we knew these measures, but we don't. So we're going to have to find the measure of angle 3. Measure of angle 3, the arc that it intercepts is 76. The arc that its vertical angle intercepts is 88. So the measure of angle 3, we would take 88 plus 76, the sum, and multiply by half, which is the same as dividing by 2. So 88 plus 76 divided by 2 is 82. It might be tempting to move on from there. However, don't forget we were asked about measure of angle 4, which is a linear pair. 3 and 4 are a linear pair. They're supplementary. So 180 minus 82. And that looks like it's 98 degrees. So our answer is 98 degrees. Number 3 asks us to find the measure of RPS. R to P to S is this angle in here. This angle is actually an inscribed angle. So that angle is going to be half of this arc. To find that arc, the whole circle is 360 degrees. And we know almost the whole circle. So if we subtract 114 and 136 from that, we would get 110 degrees is arc PS. PS. A little arc over it. Measure of arc PS. Minor arc. Less than 180 is a minor arc. So the angle that we're looking for, RPS, would be half of that. So 110 divided by 2, and that would be 55 degrees. Measure angle RPS. Our next theorem we're talking about is the intersecting secant and tangent theorem. If a secant and a tangent intersect at a point of tangency is where the tangent line touches just at one point, so that point T is the point of tangency, then the measure of each angle formed is 1/2 of its intercepted arc. This is actually kind of similar to the one we did right here. This was a secant line, and this is a tangent line. So given measure of angle STV, so this one is 71 degrees in here. Find the measure of arc TS. That would be this TS, the minor arc. It's not this TS, since that's a major arc. We would need to call that TRS, since it's bigger than 180 degrees. So the measure of this arc, if you wanted the angle, you would half the arc. But since we have the angle, we would double the angle. So 2 times 71 would be 142 degrees is TS. And then TRS is the rest of the circle, so that's simply 360 minus 142. $218. So this is 218. Another approach, maybe I'd like to see if you and your neighbor could come up, maybe one of you did a different approach than this, rather than the 360 minus 142. But I'd like you to pause and think a little bit. Is there another approach you could have used to get 218 degrees? So not sure if anybody got a different approach, but hopefully you notice that this angle in here would be 180 minus 71. That would be 109 degrees, 109 degrees. And since this is an inscribed angle, 109, you would double that and you would get 218. So that's another approach that you may have observed. Turning the page, we have, I believe, our last theorems for our chapter on circles. And they look complicated, but they're all actually saying the same thing. So let's talk about the previous theorem. If secants intersect inside the circle, so here's a circle, you have a secant line, and they intersect inside the circle. What we talked about was if this is a y and this is x, the arc here, the arc here, to find this angle alpha, we'll say, we would add the two and divide by 2. 1/2 the sum, that is. So we would do 1/2 the sum of the arcs. All these theorems, just to give the summary of the theorems, all these theorems say is if you have two secant lines that meet outside the circle, exterior, outside the circle, to find this angle, alpha, we need the measure of this arc and the measure of this arc that's formed, the two arcs that are intercepted by the secant lines. We'll call this x and we'll call this y. So all these theorems say is that alpha, in this case, is the difference of the two arcs divided by 2. So notice this, when they intersect inside, it's the sum. When they intersect outside, it's the difference. And really, all of these theorems are saying the exact same thing. Whether they're two secant lines, a secant and a tangent line, tangent, secant, or two tangent lines. So this first one says to find the measure of angle A, you would do arc DE minus arc BC, and you would divide by 2, also known as multiplying by half. This is saying the same thing. To find the measure of angle A, you would take this arc DC minus this arc BC, and you would multiply by half. And then same thing one more time. Measure of angle A is this arc formed, BDC, minus this arc, BC, and then multiply by half, or same thing, divide by 2. Notice the formula says 1/2 the positive difference. If you ever subtract them and you get a negative, it should be the positive difference. If you left it as just a difference, you could end up getting a negative angle measure, but all of these angles have a positive angle measure, not a negative angle measure. So we'd fill in the blank here with difference. If secants intersect outside the circle, the angle is 1/2 the difference of the arcs, and it's the positive difference. So I haven't shown you an example yet, but maybe you get the idea. Pause the video and see if you can find the value of x. So to find the measure of angle C, which is the value of x, we take the difference of the arcs. So that's 120. This is 50. 120 minus 50, and divide by 2. That's 70 over 2. So the angle is 35 degrees. That's all that theorem says. The next one says be careful, so you should be careful about this. Notice you're given the angle. So I'd encourage you again to pause the video. You can work with your neighbor and see if you can get what the measure of x equals. So I'm going to be very careful, since it says to be careful. We have the measure of this arc is 141. We're going to subtract the measure of this arc, x, and divide by 2. And that gives us the measure of the angle, 62 degrees. I hope I was careful enough. I don't have students to correct my work. I'm just sitting all alone. All alone. In my room. We have 141 minus x equals 124. So let's see, what would subtract? Is that 17? X is 17. 141 minus 17 is 124. So x is 17. I'd like to show you where this theorem comes from because I think it's cool. It says prove the following, that if you're given secant rays AD and AE, prove that the angle here, where the secants meet outside the circle, prove that it's DE minus BC times a half. All right, let's doctor the diagram a little bit. We're going to be using this angle. We'll call it angle 1. We're going to be using this angle. We'll call it angle 2. That angle is formed by drawing in this dashed line, which should be in your notes. That's an auxiliary line that we draw to help us with the proof. We're going to be talking about this angle 3, and we're going to be talking about this angle 4. I chose to number the angles just to make the proof a little bit more, a little easier to read. Okay, so the reason why we drew in this auxiliary line is because this angle 4 is an inscribed angle. And we know that inscribed angles are 1/2 the measure of the intercepted arc. So I know that the measure of angle 4 equals 1/2 the measure of arc DE. Again, this angle 4 is 1/2 measure of DE. We also know that this angle 4, based on the exterior angle theorem, which was a couple months ago, that angle is the sum of these two angles. So measure of angle 4 equals measure of angle 1 plus measure of angle 2. This was the inscribed angle theorem. This was the exterior angle theorem. Next, we know that the measure of angle 2, this angle right here, measure of angle 2 would be half of this arc BC. 1/2 the measure of arc BC. So we have a lot of facts here. Let's put all these together. Let's use this equation as our base. We know that the measure of angle 4 is 1/2 the arc, so we're going to substitute that in there. And we also know this measure of angle 2, so we're going to substitute this arc in here. So this is what we have. This was the inscribed angle theorem. So we would have 1/2 the measure of DE. Again, if you're wondering where in the world that came from, I'm taking this equation, I'm substituting out the measure of angle 4 for what it equals, the measure of arc DE, half of that. Measure of angle 1 stays the same. And we said the measure of angle 2, is this arc. 1/2 the measure of BC, arc BC. This theorem, we're trying to prove something about the measure of angle A, which I've called measure of angle 1. So we'd like that by itself. So we'll subtract 1/2 the measure of BC from both sides. So the measure of angle 1, let me write it like this, 1/2 the measure of arc DE minus, that's where the minus comes from, 1/2 the measure of BC. That equals the measure of angle 1. We can factor a 1/2 from each of those terms. So we get 1/2 the measure of arc DE minus the measure of arc BC, and that equals the measure of angle 1, which is the same as the measure of angle A. This is what we were trying to prove. This says that if you have arc DE and you subtract arc BC and divide by 2, that gives you the measure of this angle. I think that's a pretty neat proof. Maybe good for a bonus question. Maybe. Last question that we have says, suppose a geostationary satellite S, which you have right here, orbits about 35,000 kilometers above the Earth. There's the Earth. Rotating so it appears to hover directly over the equator. Okay. Use the figure to determine the arc measure on the equator visible to this geostationary satellite. So you're given the angle that's formed by two secant lines meeting outside the circle is 11 degrees. I said secant lines, they're actually tangent lines. Point of tangency P and R. We have this is x degrees. And there's the equator that we were talking about. But we're looking for x. So we need this measure. I'd like you to talk to your neighbor. How could we find that measure? Or what expression could we use to represent that arc measure? Go ahead and pause. I hope you said a whole circle is 360 degrees, so this arc would be 360 minus x. So now we can set up our equation based on our theorems we've been talking about. We would have 360 minus x minus x. Notice we have two minus x's in there. Divide by 2, and that equals 11. Solving that, we'd multiply both sides by 2 and combine the x's, so we have 360 minus 2x equals 22. I can add 2x to both sides and subtract 22, and solving from there. Looks like I get an answer of x equals 169 degrees. And then lastly, part B, if the radius of the Earth is 3,959 miles, find the distance from point P to R. So the distance from point P to R, that would be the arc length. So the distance from P to R, we're going to need that measure of the arc we just had, 169. What fraction of the circumference of the Earth is that? That would be 169 over 360 degrees. So how much of the Earth are we traversing there? That would be 47% of the Earth. This is 0.4694, repeating. So to find arc length, we do the measure of our arc divided by 360. I just did that and got 0.4694. And then we multiply by the circumference. Do you remember what the circumference of a circle is in terms of r? It is 2 pi r. So we'd have 169 over 360. That's the fraction of the circumference that we're traveling from P to R. And the circumference is 2 pi times, definitely not enough space, 2 pi times the radius of the Earth, 3959. Multiplying that out, we would get times 2 times pi times 3959. 11677.492. So how many miles is that? That would be a long way. 11,000 miles. If you drove from California to the East Coast, that's roughly 3,000 miles. So you would have to go, let's see, from California, here's my map of the United States, you'd have to go California to the East Coast, 3,000, and then back again, that's another 3,000, then back again, that's 9,000, and then maybe a little bit more, 2,000. So you'd have to make almost 2 round trips from here to the East Coast to be able to travel roughly 12,000 miles. Here I am. Thanks for watching this video. Thanks for understanding that my wife's not feeling well. Get to take care of her, get to take care of baby. Hope that was helpful. You can go ahead and start your homework now. Thanks again to Mr. Beauchamp for filling in. Have a great day, everyone.